So in this video we're going to look at algebraic equations and what we're calling solving for x. So I'm going to bring up three functions that we plotted on a graph in the previous video, and if we look, for example, at this function here, function y equals x plus 3, then we can see that this is an equation. We've got the equals sign here. What does x plus 3 equal? It equals y. And y is this variable that we said was a dependent variable. Y depends, what y is, depends precisely on what value we have for x. Now if we draw a line across here and fix the value of y, so if we draw a line that we're going to call y equals 8, so that's the line y equals 8, what we're doing is fixing the value of y for this function at y equals 8 and asking ourselves, well, if y equals 8, what does x equal? In other words, what we've got is the equation. Let's go over here just to write this out. X plus 3 equals not y anymore, but the fixed value 8. And we probably can immediately see that if x plus 3 equals 8, then x must equal 5. So we can jump straight to the answer there, because we know, I suppose from infant school, that 5 plus 3 equals 8. So we know this as a number fact, if you like. But there's no method here, and as these expressions get more complicated, this method is going to let us down, and it causes an awful lot of mistakes and errors and just consternation in exams. So we need something more systematic to arrive at our solution for x. If, for example, we take, so let's call this a, if, for example, we take 2x plus 1, and again fix that equal to 8, so fix it at this point here, equals 8. Then we could substitute in, let's say, 3, so 2 times 3 plus 1 is 7, so that's not enough. We could then think, well, what about 4? 2 times 4 is 8 plus 1, so that's too high, so it must be between 3 and 4, so x must equal 3.5. So we can do this mentally, but you can see how that was much more difficult to arrive at the answer than the simpler problem that we had here. Okay? We can check that these answers are correct, by the way, by just reading off from the graph. So when y equals 8 for the function y equals x plus 3, x does indeed equal 5. And for this function, when y equals 8, we can just read down here and see that 2x plus 1 equals, when we've got 2x plus 1 equals 8, x must equal 3.5, okay, 3.5. So we can read off from our graph, which is another way, I suppose, of solving these problems. But if we don't want to write out draw out a graph, which takes a fair bit of time, then we ought to be able to trust our algebra. Now the algebra that we're going to use here is called rearranging. Rearranging equations. And we need to become fluent at doing this so that we can work with any problem that we're given, problems that will end up being much more complicated than this. So let's rethink this. Let's try b again. 2x plus 1 equals 8, and we're going to solve for x, this time using algebraic rearranging. Okay, well, what can we do? If we had something, if we go back to this, in fact, if we have x plus 3 equals 8, and we think about what we're actually doing to arrive at x equals 5, then we want to remove this from the left-hand side. We want to end up with x equals 5, but 5 equals 8 minus 3. So we should note from this, we might just see immediately that what's happened is when we've moved that 3 where we've removed it from the left-hand side, we seem to have moved it over to the right-hand side, changing its sign. In other words, what we've got here is the inverse of adding 3. We've got the subtraction of 3, so 8 minus 3 gives us our answer of 5. So this gives us a method. We could just think that, well, if we move one of the terms to the other side, we just change its sign or perform the inverse operation, and then that should work out. A better way of thinking about it, in fact, is, well, what did we do? What we actually must have done is we must have subtracted 3 to remove that 3. So to change the sign, in other words, and just remove the 3, we subtracted 3 from the left-hand side. We can say minus 3 plus x, and then we cancel these 3 because minus 3 plus 3 equals 0. Now, if we need to have minus 3 on the right-hand side, then we can see what's happened is we've subtracted 3 from both sides. So we subtracted 3 from the left, meant we had to subtract 3 from the right. So we end up with the rule that whatever we do to one side of an equation, we have to do the same to the other side, if you like, to preserve the balance of the equation. Otherwise it becomes unequal. So thinking about that idea, if we go back to this, we have 2x plus 1 equals 8. What do we actually want to do? Well, we want to remove the plus 1 from the left-hand side. So we think of the inverse operation, which is subtracting 1. We'll end up on the left-hand side with 2x plus 1 minus 1. And on the right-hand side, 8 minus 1 as well. So subtracting 1 from both sides. On the left-hand side, this 1 and this minus 1 then cancel. And so we have 2x equals 8 minus 1, 7. Now we're nearly there. We want to have the answer, if you remember, 3x equals 3.5. We're now multiplying by 2. So we could rewrite this, if we wanted to be pedantic, 2 times x. So what do we need to do to remove that 2 times? Well, if we divide by 2, which is the inverse of multiplying by 2, then that will remove that 2 from the left-hand side. So we have now 2 times 2 divide by 2. So we're going to, in other words, divide by 2 on both sides. And we can write this like this. Divide by 2, divide by 2. So exactly what happens on the left-hand side must also happen on the right. So let's remove that times operation, which we don't tend to use in algebra. So we just have, there we go, 2x divided by 2 equal, 2x divided by 2 equals 7 divided by 2. And now what we can do is cancel these 2, because 2 divided by 2 is 1, and 1 times x is just x. So we have our answer, x equals 7 halves, or 3.5. Okay, so that's really all there is to it. What we're going to do now is work then on this equation here. So if we think of that, it'd be over here somewhere, probably off the screen a little, or just at the edge of the screen. If we think of that again as fixing the y value to 8. Okay, what have we got? We've got half x plus 2 equals 8. So how are we going to do this one? Well, I'm going to show you 2 methods here now, in fact, because one of these, one of the important ideas is that there isn't just one way to solve a problem, and we ought to develop enough fluency to be able to solve problems in different ways. How we do it, how we want to do it, not necessarily how we ought to. That way we can avoid just trying to remember some method that we were taught. But also there's an important idea here that I'm going to introduce that will be very useful later on. It won't be particularly useful now, but it's worth looking at now so that we can see, so it doesn't come as such a surprise later on. So what I would naturally want to do, if I wanted to solve this, is I'd want to remove this plus 2. Okay? And we could do that simply by subtracting 2 from both sides. So plus 2 minus 2, we'll just remove it from the left-hand side. And if I subtract 2 from the left-hand side, then I must subtract 2 from the right. So I end up with half x equals 8 minus 2 equals 6. Okay, half x equals 6. If half x equals 6, I can now multiply by 2. In other words, if I write it this way more correctly, if I multiply by 2, I'll end up with 2 times 1 in the numerator here. I'll end up with 2 times a half, which is just x. And if I multiply by 2 on the left-hand side, multiply by 2 also on the right, I end up with 2 times 6. In other words, these cancel, I end up with x equals 12. Now, the other method that I said I wanted to introduce may not be quite as efficient as this, but as I say, it's another way of doing it, and it will be a useful method later on. So let's have a look at that. Okay, so half x plus 2 equals 8. We said we can remove this to start with, but another idea would be to remove the right-hand side, the 8 here. So how would we remove the 8? Well, just by subtracting 8. So if we subtract 8 from both sides, we'll end up with half x plus 2 minus 8 equaling 8 minus 8, in other words, 0. So we've rearranged this in a slightly different way to the way we rearranged it over here. Okay, what do we do next? Well, we always simplify if we can. So we've got half x, now subtract, so 2 minus 8 gives us minus 6 equals 0. And now we're in a similar situation to the one that we were over originally here, in fact. So what we want to do is remove this negative 6. So we add 6, giving us a half x, minus 6 plus 6, so just a half x. And if we add 6 to the left-hand side, it must mean that on the right-hand side we have 0 plus 6 equals 6. So if half x equals 6, just as we did before, we multiply through by 2. So 2 times half x will just give us x. 2 times 6 gives us 12. So this is called putting it equal to 0, and putting it equal to 0 can be a really useful method, even if we probably wouldn't use it in this situation. Okay, finally, what I want to do is look at what would happen if we, instead of just fixing the value here, so looking at what happens when y equals 8 coincides with y equals x plus 3, for example. What about these situations here where we have two functions which coincide, called simultaneous equations? Could we resolve these in a similar kind of way? Well, we ought to be able to. It just requires a little bit more rearranging. So what I'm going to do is just erase what we've done before here, give ourselves a bit more room. Okay, so I think I'll just erase a couple of these things. Okay, and let's have a look at those functions then while I'm erasing my working here. What we've got, I think the simpler one to begin with would be, let's just remove that there like that, would be the y equals 2x plus 1, and the point where it crosses y equals x plus 3. Okay, so there we go. Let's just remove all of that as well. There we go. Okay, so this point here then, and at this point y equals 5. So when these functions coincide, it's when both y values equal 5, and if the y values are equal to one another, then the expression must also be equal to the other, to each other. So we end up with, let's call this d2x plus 1 equaling here x plus 3. So again, you wouldn't want to do this by substitution, although you could. You'd want to simply apply the rules of rearranging equations. So how are we going to do this? We have a number of choices. We could put it all equal to 0. Let's try that to start with. So let's say we subtract x plus 3 all in one go from both sides. Okay, that would be an interesting way to proceed. So what would we have? We'd have 2x plus 1 on the left hand side minus, well, all of x plus 3, so we have to put that in parentheses. Okay, and on the right hand side, x plus 3 minus x plus 3 gives us 0. So now expanding the brackets, we have 2x plus 1 minus x minus 3 equals 0. Simplify the terms, so gather the like terms together. We'll have 2x minus x giving us x, and 1 minus 3 gives us minus 2. So we have x minus 2 on the left hand side equals 0. And if x minus 2 equals 0, then x must equal, well, add 2 to both sides. So add 2 to minus 2, we end up with just x, and 0 add 2 equals just 2. Okay, so that's when we put it equal to 0. Let's try the other method, see if it's any easier. So we have 2x plus 1 equals x plus 3. This time, let's do it in a couple of steps. Let's try and move the x to the left-hand side and move the numbers all to the right. So we might start with the numbers here. So we've got 1 minus 1, and we've got 3 minus 1 as well. So we've got 2x plus 1 minus 1 on the left-hand side equals 0. So just 2x, and x plus 3 minus 1 gives us just 2. So x plus 2. So that's subtracting 1 from both sides. Now we're going to subtract x from both sides, which will remove this x. So 2x minus x gives us x on the left hand side, and x plus 3 minus x will give us just 3. So x equals 3. Okay, so sorry, not 3, x equals 2. Okay, x equals 2. So this method seems to be the easier one, but bear in mind this idea of putting everything equal to 0, because, as I say, it's going to become a very useful method later on. All right, now for, let's call it E. So we have a simultaneous equations here. So this is where two functions coincide. So we have, as an equation, half x plus 2 equaling, the other function is 2x plus 1. And in fact, where here y was equal to 5, it's not even clear what the y value here is from our graph, and it's certainly unclear what the x value is. So using the graph wouldn't give us a very reliable method. Okay, whereas here we can check that x equals, certainly does equal 2 when y equals 5. But here we've got to trust our algebra. So this is a good test of our algebra. Is our algebraic methods going to work? Okay, this time, well, let's try both methods again. So we're going to have, first of all, we'll put this equal to 0. So we have half x plus 2 minus 2x minus 1. So we just skip that step there and just go straight away and subtract both the 2x and the 1, equal to 2x plus 1 minus 2x plus 1, in other words, equal to 0. Now we have to gather terms, so we have minus 2x plus half x will give us minus 3 halves of x on the left hand side, and we have to gather this term as well, these terms as well, so the constants. So we have 2 minus 1 gives us plus 1. Okay, very simple now to move the 1 over to the right hand side. We just subtract 1 from both sides, so minus 3 over 2x gives us minus 1. We could, if we like, at this stage, multiply through by minus 1, and that's a really nice trick. If we have negatives on both sides, this is a very good method. So it just allows us to remove the negative signs. So I can just use an eraser for this. So we just erase those negative signs, and we did that by multiplying through by 1. Okay. Now, there are a couple of ways to proceed here, but I'm going to just pause at this stage because I want to rearrange this in the simpler way that we had here. So see if we can get to the same stage. So we start with half x plus 2 equals 2x plus 1. Exactly the same way. You might want to pause the video here, in fact, just to try this yourself. So what are we going to do? Well, first of all, we want to gather the x's on the left-hand side and the numbers on the right. We could do it the other way around, but it's just neater if we have the x's on the left. So to move the x over to the left-hand side, we subtract 2x. So we'll have half x minus 2x on the left-hand side, and to get this onto the right-hand side, we are subtracting 2 from both sides, so we end up with 1 subtract 2. Okay, so that's gathered the x's on the left-hand side and the numbers on the right. We now need to simplify. Whoops, missed out an x there. Half x minus 2x. So what's half x minus 2x? Well, we might want to just rewrite this. Half x minus 4 over 2x to make this easier equals 1 subtract 2. Because we know that subtraction we need common denominators, so now we've got half minus 4 halves giving us minus 3 halves of x equals minus 1. So 1 minus 2 is minus 1. Again, we can multiply through by minus 1, so minus 1 times minus 3 over 2x gives us just 3 over 2x, and minus 1 times minus 1 gives us just 1. And we've ended up with exactly the same, at exactly the same point here. Now, what are we going to do just to finish this problem? How do we resolve 3 halves of x equals 1? There are 2 ways. So I'm going to, on the left hand side, look at one way, and on the right hand side look at another. So we can rewrite this. Whoops, let's just erase that little error. If we think about this as simply 2 things going on here, we can rewrite this 3x divided by 2. So we've got the numerator of this fraction, if you like, is also a multiplier, so it's 3 times x, and the denominator is also a divisor, so we've just turned that into divide by 2. Okay, so I don't need to do anything to the right hand side because all I did was just sort this out a little. But now what we can do is we can multiply through by 2, so we can multiply by 2, which will remove the divide by 2 here, giving us 3x equals 1 times 2 on the let's put it here, times 2 here on the left hand side, so we multiply by 2, cancels those 2's, and now we've got 1 times 2 on the right hand side, giving us 3x equals 2. Okay, and finally we can divide through by the 3, giving us x divided by 3, so let's write it out like this, 3x divided by 3 cancels those 3, giving us just x equals 2, also divided by 3. In other words, x equals 2/3. Okay, so that's one way of thinking this through, but I'm going to try a slightly easier method. When we've got a fraction like this, it's useful to do it in one step. So I'll show you what I mean. If we think of this as 3 halves, just keep it in fractional forms, what do we need to multiply 3 halves by to end up with just 1 so that we can cancel on the left-hand side? Well, we need to multiply by 2/3. So instead of thinking about this in terms of multiplication and division, we're just multiplying by the fraction 2/3. We end up with, let's write this up here, 2/3 times the 2, and so we multiply by 2/3 on the right as well. We end up with 2/3, sorry, let's just erase that. We end up with 2/3 times 3/2, so 3 halves. Well, we can cancel the 2 here, we can cancel the 3 here, we end up just with x. Or we might think of this as multiplying across. 2 times 3 is 6, 3 times 2 is 6, so 6/6, and again 6/6 is 1, and so it just comes out as x. So we had to multiply the left-hand side by 2/3. And on the right-hand side then, we've got to do the same, so 1 times 2/3 is simply 2/3. So it's up to you how you think about these problems and how you rearrange them, but the aim is always the same. We need to isolate the x on one side of the equation, and on the other side we need a numerical answer. Okay, so in the final part of this video I'm just going to work through a few visualizations. So the key skill is clearly to do with rearranging the equation, and the equation here is represented by a balance. In other words, what we have to do when we're rearranging is always maintain the balance of an equation. So what we've got here, if we just write this out, we've got 2x tiles and a 1, so we must have 2x plus 1 on the left hand side, and on the right hand side we've got x plus 3. So we're going to just keep an eye on what's happening with these manipulables and just follow through with our algebra. Okay, so let's see what happens in the algebra animation. And I think what's going to happen, I'm not entirely sure, but I think what's going to happen is we're going to remove this isolated 1 here, so we just end up with x's on the left hand side. If we remove the 1 from here, we should end up with removing 1 from here as well, so that will maintain the balance, so we should end up with x plus 2 over on the right hand side. Anyway, let's have a look. So we remove this one, do we? There we go. So we've removed 1 from both sides, and we end up with 2x plus 1 minus 1 is just 0, so we just end up with 2x on the left hand side, and on the right hand side you can see we've got x plus 2 because we removed one of those 1s. Okay, so the next operation is we need to get down to just 1x on the left hand side, so I guess if we remove an x from both sides like this, yeah, there we go, then we end up with x equals 2. Okay, x equals 2. So what did we do? We simply subtracted x from both sides, so minus x from this side and minus x from here meant we could cancel here, and minus x plus 2 equals x. Okay, so that was fun. Let's do another one. Okay, now, there we go. What have we got now? So this time what we've got is on the left hand side we've got 2x plus 1 again, but on the right they've introduced a fraction, so we've now got half of an x, so half x plus 2. Okay, so again probably what we want to do first is remove that 1, so let's see if that, yeah, that's indeed what happens. So we've now got 2x equals half x plus 2 minus 1, 1. Okay, so that's subtracting both sides by 1. And now obviously what we want to do is remove one of these x's, but if we remove that x, well, half x minus x, let's see what happens in the animation. There are various ways that we could approach this, but let's see what's been set up here. So, okay. So the strategy here, interestingly enough, was simply to subtract half x from both sides. So once the half x had been removed from this side, like that, then they had to subtract half x from this side as well. So they end up with half x plus 2x gives us 1.5 of x. So I don't want to write that 1.5 times x. Let's just see what happens in the animation to see where we go next with this. Okay, so what we want to do, if I can just show you actually, what we want to do is remove, there we go, remove that half, okay, to end up with just the x. And so the question, there we go, get it back again. The question is, how do we do that? Well, the first thing that we've got to do is think of this as 1, 2, 3 halves. So, okay, so the animation is leading us through here. In other words, half x plus 2x is the same as, if I just erase this just to save space here, keep it nice and neat. We had 2x there, that's the same as 4 half x, and now we have 4 halves of x minus half of x gives us, so common denominators, gives us 3 halves of x on the left hand side. Okay, so that's what we've got here. And on the right hand side we've got 1. What happens next? Well, what happens next is that we can now remove half of an x. And what does it mean that we've done there? We've multiplied by 2/3. Let's just have a look at that again. So if we had 1, 2, 3 halves, 2/3 of 3 halves, well, they are in thirds now, 1, 2, 3, so 3 equal parts. So 2/3 of 3 halves is 2 halves. There we go, which is just x. Okay, so that's a visualization of that, and what happens on the right hand side must also happen on the left. So yeah, here we go. We've now got, let's write it out here, we've now multiplied by 2/3, so 2/3 times 3 halves of x, and 1 times 2/3 gives us on the left hand side just 2 halves of x, in other words x, and on the right 1 times 2/3, in other words just 2/3. Okay, so that was a nice easy one. It gets a little bit trickier with fractions, but as long as you know what you're doing, as long as you understand how to deal with fractions, then it's reasonably straightforward to get the answer. Now, one more I think. Let's just erase this and see if we can come up with something interesting just to finish with. I'm not quite sure what happens next. Let's see. Okay. So what we're doing now, and this is a very useful one to finish this video with, is we've got, well, on the left hand side, x minus 1, so this is representing a negative, and on the right hand side we've got 2 negative x's plus 2. So in other words, minus 2x plus 2. And so we haven't had an example like this before, so it's a useful one to finish where we've got a negative coefficient of x. How would we deal with that? Well, I think what we would probably want to do, first of all, is we would want to get rid of this minus 2x. And we would get rid of the minus 2x just by adding 2x. So that would remove it from the left-hand side. And if we do that, then we're going to have to add 2x to this side as well. So we should end up with 3x minus 1 on the left hand side and just plain old 2 on the right. Okay, let's see if that works. So we're going to add 3 to this side. And with algebra tiles, what will happen when we add 2 to this side, 2x's, the positive x's and the negative x's should cancel each other out, so we should see them dissolve, and we end up with just the 1's here. So let's see that see if that's what happens. So we're adding 2x here, and yes, sure enough, on the right hand side, the 2x's that we added dissolve the negative x's. Okay, so what have we got? We've ended up with 3x on the left hand side minus 1, and on the right hand side simply 2. Okay, so just to finish this then, what we'll need to do now is remove that minus 1. So if we add 1 to both sides, we should again see this negative being cancelled by a positive 1, and then we should have an extra 1 on the right hand side. Let's see if that's what they show us. Okay, yep. So now if we write this out, we've got 3x equals 3. Okay, so all we did was added 1 to both sides. And finally, how do we get down to the answer? Well, we need to divide this time by 3. So we have 3 times x divided by 3. So divide left hand side by 3, the right hand side by 3, and we should end up with x equals 1. Let's have a look. Okay. There we go. Alright, so that ends this video, but what I'll do is a practice video where we'll again use the idea of functions and the intersection of two functions as a way of practicing setting up lots of equations rather like this, and then see if you can resolve those in the practice video.